Hello and welcome to lesson 1.3 related rates. So today we're going to see how a rate is possibly related to another rate within an expression. So what I'm going to do is I'm going to show you using the function a equals pi r squared, and what we're going to do is we're going to calculate the derivative of this with respect to both r and t. So if I take this derivative of a with respect to r, using implicit differentiation, I get 2 pi r times dr of dr, which we get as just 2 pi r, because the dr over dr just cancels. However, if I do take it with respect to t, I get dA dt, and this is 2 pi r times dr dt. And here we see that the rate dA over dt is related to dr dt in some format, in some fashion. And that's what we call a related rate. So what we're going to be doing is we're going to be looking at problems that deal with possibly drawing a diagram and labeling only constants as values, and using variables for other measurements. Usually what you want to do is you want to find something given something when something occurs. So you might be finding a volume, let's say, when a height is given at a certain time. Now this requires to write an equation using variables for which you have the rate, or have to find the rate. If you have any extra variable for which you are not given the rate of, or not required to find the rate, find the relationship between the variable and the other variables. So sometimes that is a really tricky part to find. I'll show you an example of something like that in just a moment. We're going to differentiate both the sides of the equation with respect to time. Then we're going to substitute the given and when values, and then solve for the find. Make sure you do this after finding the derivative. So don't ever substitute the values in beforehand. And then write a conclusion based on that information. So let's take a look at our first problem. So a spherical snowball is melting at 1 centimeter cubed per minute. So there's a rate. So first of all, that I'm just going to write as, because it's a spherical snowball and it's melting at 1 centimeter cubed per minute, that's a volume. So the volume with respect to time is, and I'm going to say -1 centimeter cubed per minute, because it's melting. The next part of this says, at what rate is the radius decreasing? So here it says the rate at which the radius is decreasing. So we need to find dr dt. That's a question mark. When the radius is 5 centimeters. So there's the other portion of it. It tells you that the radius is actually the value of 5. So, do you know of any relationship between volume and radius? Well, hopefully you remember the volume of a spherical, or a sphere, is 4/3 pi r cubed. So now we find the derivative with respect to time on both sides. I'm going to write it this way to start with. So this turns out to be dv over dt, and this part just turns out to be 4 pi r squared times dr dt. Again, got to use implicit differentiation here. If you don't use implicit differentiation, it may not work. Okay, so then we substitute our values in at this point if we happen to know them. So dv dt we know is -1. The value is 4 pi. Radius at this time is 5, so put 5 in there. Squared. And we're looking for dr dt. That's the only thing that we don't have. So at this moment in time, it's just a matter of just going about and solving it. So we rearrange the expression. dr dt equals to negative 1 over, now 5 squared is 25, 25 times 4 is 100, so this is going to be 100 pi that we're dividing off of. And now you find dr dt is actually a value that's decreasing, so now you can write your conclusion. So therefore, radius is decreasing at 1 over 100 pi centimeters per minute. Don't forget the units. Notice I don't write the negative there. It's because I'm already using the term decreasing. Okay, so let's try the next problem here. A water tank is built in the shape of a circular cone with a height 5 meters and diameter 6 meters at the top. So it tells you actually what the cone looks like. Water is being pumped into the tank at a rate of 1.6 meters cubed per minute. Find the rate at which the water level is rising when the water is 2 meters deep. So this one I'm going to actually draw a diagram to go along with it. So I'm going to start out by drawing a cone. Okay, so we have a height of 5 meters, so I know this entire height of this cone is 5 meters. I know the diameter is 6 meters at the top, so that means just the radius, because usually we're just looking at radius when we're talking about these kinds of things, is 3 meters. Now I have the water being pumped in, so water is coming in at 1.6 meters cubed per minute. And that means when the water is filling up, it's going to give you some kind of like cone-like shape inside the cone. And say this is the top of the level of the water. But what I'm going to do is I'm going to draw a small triangle right here that we got. Now this height right here constantly changes, but so does this radius right here. This radius is constantly changing. So that h and that r, although we know the height specifically when it's 2 meters deep, do not put the value 2 in just at this moment. But you do realize, due to the fact that this right angle red triangle that we have here, and this right angle triangle that I'm drawing right in here now, in purple, is similar, then what we can say is h over r is equivalent to 5 over 3. Now I'm not going to do anything with this at this moment. I'm going to work this out in a second, but I realize there is a way that the volume, this is what's given, dV over dt, is 1.6. I want to find at what rate the water level is rising. So here I'm looking for dH dt, that's the unknown, and this is when h is 2. So I have to have a way that volume is related to height, not volume and radius, but we do know something that cannot help us with there. So I know the volume of a cone is given by 1/3 pi r squared h. And it shows in here volume is related to radius and height. So we have to figure out how to change it so that it's just related to height only. So what we're going to do is we're going to take this value that we have over here, this h over r equals 5/3. I'm going to rearrange it so that r over h is 3/5, and r is 3h over 5. So that means now I can take that radius and substitute it into my formula. And I can simplify it, and now I got an expression for volume in terms of just height. So I'm going to simplify this. This is 1/3 pi. This is 9h squared over 25 times h. So this volume now turns out to be just 3h cubed. 3 pi h cubed. Let me fix that. H cubed over 25. Now with this, now we can find the volume, or the rate. So again, I apply the volume, or derivative with respect to time on both sides. So this is dV over dt is equal to 9 pi h squared over 25 times dh dt. Okay, so now I can substitute the values I know. So I got 1.6, I'm going to put 1.6 over here, I put 9 pi, h is 2, square that, over 25, dh dt. Okay, so now it's just a matter of solving this. So solve for dh dt. So 25 times 1.6, well I know 25 times 4 is 100, and that's got a 0.4 in there, so that's going to be 10. 10 times 4 is 40, so this is going to be 40 over 9 times pi times 4. I'm going to leave it like that for the time being. I'm going to change it. Now I'm going to cancel out the 4's, so now I get 10 over 9 pi. So there's my change in my height. So now I can write a conclusion. The rate at which the height is changing is 10 over 9 pi. This was measured in meters per minute. And there we go for that example. Okay, let's take a look at our last example here. So a person is 500 meters away from a launch point of a hot air balloon. The hot air balloon is starting to come back down at a rate of 15 feet per second. At what rate is the angle of elevation changing when the hot air balloon is 200 feet above the ground? So as you can see, I got a little diagram already started to draw here. I have the person's point of view. I have the theta as the angle of elevation. I have where the balloon is at the moment, but it's coming down. And you can see the little arrow right there. So that little arrow is measuring 500 feet per second. Oh, my apologies, that was 15. I wrote that wrong. 15 feet per second. You can write that as a negative or whatever, but you know it's falling, so I also know this distance right here is 500 feet. Now specifically, you know the height is 200 feet at the specific time. So let's call that h, which is 200. I know the rate at which it's falling, let's call it dh dt is negative 15. Okay, so I have to have some kind of relationship with this angle theta and this length here and this 500 feet here. No, I know tan theta is equal to h over the distance, which is 500. Now because I have the specific value of 500, I'm going to write that in. Okay, so now I'm going to find the derivative with respect to time on both sides. Okay, derivative of tan theta, I remember secant squared theta, and I'm going to multiply by d theta dt. Derivative of h over 500 is just 1 over 500 times dh dt. Now, at this moment, it doesn't look like we've used the 200 at all, but notice that this derivative is in terms of secant squared theta. I don't know what secant theta is or secant squared theta in this expression at all. So, remember, sine squared theta plus cosine squared theta is equal to 1. If we divide everything by cosine squared theta, I get tan squared theta plus 1 is equal to secant squared theta. So now I have a relationship between secant and tan. Okay, so if tan theta is h over 500 from our original expression, and we wanted at that specific time of tan theta is 200 over 500, then I know tan theta is just 2 over 5. Okay, so now secant squared theta is 2/5 squared plus 1. Okay, so this is going to turn out to be 4 over 25 plus 1 equals secant squared theta. And secant squared theta is now the value of 29 over 25. Okay, so now we have all our pieces. We can just solve for dh. We can solve for d theta dt. So put d theta over dt here. Secant squared theta is 29 over 25. We got the 1 over 500 there. And the dh dt is negative 15. Okay, so whenever you do this kind of thing, don't simplify first. Just try to rearrange. Might be better to simplify afterwards. So I get negative 15 over 500 times 25 over 29. Okay, well, right off the bat, I do notice that 25 and 500 have similar terms. So I can divide 25 into 25 once. I can divide 25 into 500 20 times. I can also reduce that negative 15 and 20 to negative 3 over 4. So now this expression is just going to be negative 3 over 4 times 29. 4 times 30 is 120, put 4 off, so 116. So this is feet per second listed there. Now we can write a conclusion. So the balloon is, it's the angle of elevation. The angle of elevation is reducing, and it's not actually feet per second, that's radians per second. So reducing by 3 over 1/16 radians per second. And there we go. That's how we do that problem. And thus concludes this lesson.